Let's get started. Okay, we're class 35. That means that there's 6 more after this. Time really flies, right? So homework 12 is due on Monday. We're going to go over the last of some cost estimation concepts that play into that assignment. And then Friday of next week is when your project is due. I'm anxious to help you on your project, but I am busy with a lot of things, and so I may not be able to debug spreadsheets. So that's not one service I'll have the time to do next week, at least not via email. If you stop by my office hours, I'll be happy to look things over, but just based on the volume of requests I know that I'd get, I can't tell you whether your work is correct or incorrect just from an email request. I won't be able to pre-grade student work outside of my office hours. And so if you do feel anxious about it and think you may have a mistake and want to double check on that, I'm happy to see you during my office hours next week. Today we're going to be talking about some additional concepts from chapter 15, cost estimation. And so that includes cost capacity equations, the factor method, activity-based costing. So this is important stuff, and I, as always, encourage you to review the lecture material afterwards and the related concepts in the book. So any questions related to the announcements? So let's just real quick talk about a couple of key ideas from the homework assignment. So I've included this as a hint on how to calculate the total cost on problem 7. So this is something that we'll talk about today. We're going to talk about indirect costs and direct costs, and how major equipments can be a baseline cost for the overall project cost. So I'll show you this formula in a bit, but so you don't need to furiously copy it down right now. I just wanted to clarify that this is the problem 7 formula that you use, and then in problem 8 you're going to be applying the cost capacity equations, which we'll talk about today, and also applying the cost index ideas, which we did in a previous class. So I think we did the cost index stuff on Monday, and today we're going to do the cost capacity. So cost index is adjusting for changes in price over time. Cost capacity is related to changes in price as a function of size. So if a project that you're predicting the cost for in the future is going to be both a different size than your previous project and also at a later time, then you need to correct for both of those factors. So just a couple of hints for the homework. Also, I think there may be a slide that, here we go. I wanted to talk about the final exam. We still have a ways yet, but just to put it on everyone's radar, we're going to have our final exam the second to last time slot. So that's on Friday the 8th, and it's at 10:15 a.m. So the final exam will be comprehensive, but there are going to be disproportionately more points on the exam, and more material on the exam will be related to the content that have been covered since the second midterm. So there will be questions on everything through the semester. And the material itself is naturally comprehensive, so it would be impossible to have it any other way. But more of the points will be on the more recent material that you haven't yet been examined on. Also for that final exam, you can bring 2 pages of your own notes, and then I'll provide the same formula sheet that I've given you on the first 2 exams. So, the equations related to time value of money and the factor table where it's needed. And then for the final exam, you'll need to bring your laptop again, because there will be some questions that you should solve with Excel that can't be solved by hand, where I'll specifically tell you that it needs to be solved with Excel. So plan on bringing your computer to the final. Okay. If you're ever flying and look down, you may notice these big pools, and they're not swimming pools. They're wastewater treatment plants. So never make the mistake and accidentally dive into one of these. You'd be sorely disappointed. What we're looking at on the left, these are aeration basins where sewage has air bubbles pumped through it to try and break down some of the pollution. And then these circular ones are clarifiers, where waste particles settle to the bottom of the tank or float up to the top and are removed to try and purify the water before it's discharged to a river. You'll send water to a treatment plant like this, and this is a pretty big one. And so the question can be, if you have cost data for this big wastewater treatment plant, how could you use that cost data for a much smaller treatment plant that has fewer clarifiers, a smaller aeration basin? Are there adjustments that need to be made that are irrespective of differences in geography and aren't necessarily related to changes over time, but just strictly have to do with the size relationship? And we've talked about this idea before, the idea of some things become less expensive as the more of it you buy, but we can do better than just that generalized idea. There are tables that tell us the precise relationship for certain categories of items between size and increases in cost. And so we can go to those tables and look up the correlating exponent. So the correlating exponent for an aeration basin would be different from the correlating exponent for a sand filter. And the correlating exponent for a air diffuser assembly would be different from the correlating exponent for a pump. So just any piece of equipment that you can think of, whether it's wastewater treatment or robots or ingredients for baked goods, there are these correlating exponents that basically take into account the linearity or nonlinearity of cost relationships. So this formula basically says if you have the cost data for one item, so C1 was the cost of the item that you already know about, and Q1 is how big it was. So it could be units of flow rate if it's a pump, or it could be units of square feet if it's some sort of a surface filter, or it could be units of weight if it is a quantity of something that you'd measure it in that sense. Q2 is the size of the thing that you're trying to predict the cost for. So item 2 is the item that you're trying to predict the cost for. And so you take the ratio of the sizes to the power of the correlating exponent and then use that to predict what is the cost of the second item. So when x is less than 1, that's what we call an economy of scale. So it's the classic figure that I think you've seen the chart for in a previous lecture when we were talking about fixed costs and variable costs. We were looking at a curve that flattens out over time, where this is cost, this is size, and this is cost. Boy, all of these markers in here are just dried out. So when you have x less than 1, that means that if you double the size, it's not going to double the cost. It would be less than a doubling of the cost to double the size. Whereas when x is greater than 1, that means there's a diseconomy of scale, which means there's actually some sort of a penalty for some reason in getting larger. So the example I gave before was like vertical construction of high-rise buildings, where a 20-story building is likely to be more costly on a per square foot basis than a 10-story building because it becomes increasingly complex to build up in the sky. And then when x is 1, that means that there's a linear relationship, that there's no effect related to cost based on increasing size. Okay, so just as an illustration of how we would apply this data, if you knew that the size of a water treatment plant was 0.5 million gallons per day, So that's how much it's sized to treat. Then that would be Q1. So we'd say Q1 is 0.5 MGD. And we know that that cost, C1, was $1.7 million. And then we want to know what is the cost of a plant that has a size of 2.0 MGD. And so C2 is the unknown. And water treatment plant has a correlating exponent of 0.14. So X is 0.14. Then to predict C2, what we'd say is it's C1, which is the $2 million that we know about. And then it's the ratio of the sizes. We're going to be trying to, I'm sorry, the cost was 1.7 million. 1.7 million was the cost. Now the ratio of the size is 2.0 MGD divided by 0.5 MGD. And then we take that ratio to the power of 0.14. So does anybody have a calculator handy and tell me what is 2 divided by 0.5 to the power of 0.14? Just double check to see if we get the same numbers here. Do you get 1.23? So it's $1.7 million multiplied by 1.2311 and so on. So that means that the cost of this larger water treatment plant that we're trying to estimate the cost for is going to be $2.09 million. That would be the cost of the larger one. So that's not much more money. You're quadrupling the size of the treatment plant. You're going from 0.5 MGD to 2 MGD. So 4 times as much capacity for just a tiny fraction of added cost. That's, I guess, the beauty in this case of having a really low correlating exponent, is there's a huge economy of scale. Any questions about that idea?
So in this instance, why would you want to build a smaller version of it? Because you're going to eventually need to build a larger version anyway.
Maybe not. You know, it could be that the area that you're at is already fully developed. You know, like if you're replacing a wastewater treatment plant and it's already completely urbanized, then maybe you won't need a larger wastewater treatment plant than 0.5. And so the advantage would be just build the one that you actually need. But you're right that in a lot of areas that are developing, that they may need more capacity later on down the line. So this is something that they should always look at when they're planning, whether it's a building or any kind of infrastructure or equipment, is how much extra is it going to cost you to get a larger item? The next size up, is it maybe worth getting it now and making that investment?
So does this take into account, like, say if you have excess, the money that you can, so say if it's big enough to the point where it's accomplishing everybody's need in its service area, if it were to take on more service areas and stuff like that, like I know Milton's wastewater service plant does that, this does not help with the cost or count that in?
Well, this doesn't take into account how much the thing is going to be used. It's just taking into account the price of it. Yeah. So this shows correlating exponents for a variety of different water treatment plant equipment. So it's got correlating exponents you can see for chlorine treatment, for a clarifier. So most of the things on this list have a correlating exponent of less than 1, which means as you increase in size, it's becoming progressively less expensive on an incremental basis. So, you know, with the correlating exponent of 0.14, that's the same correlating exponent that we just had. That means you can quadruple your size for just a little bit more money. But the closer the correlating exponent is to 1, so like a clarifier, you don't get much of a discount with the clarifier for doubling the size. It would be approximately double the price. And then there's a handful of things here where the correlating exponent is greater than 1. So you see sludge drying beds has it greater than 1, the aerated lagoon, the laboratory. All of those are things where the cost is largely based on the amount of surface area required. So every kind of equipment and project likely has similar data. It's not only for wastewater treatment that this kind of data is available for. It's just a matter of getting a hold of it. But this can be a really effective technique for looking at the effective size.
Where do they find this information, and how do they like create this information? Like, do they just grab data and just compare it, or like, is there a formula that they use?
They would fit it to this. So they like you could find the correlating exponent yourself by going through materials catalog or calling a supplier. You know, like if you called Lowe's and said, how much is it to get 1 bag of shingles? How much is it to get a pallet of shingles? And then you'd have, you know, C1 is the cost of 1 bag of shingles, and Q1 would be like the number of shingles in a bag. Q2 would be the number of shingles on a pallet. C2 would be the cost of the pallet. And then if you have all the cost data for 2 different items, then you could calculate what is X.
So you would have to also consider like transportation costs and those as well. Okay.
Yep. All right. So let's practice that. Let me pause the recording and hand out the in-class exercise.
So this one is a smaller chart.
The correlating exponents is on the back side of the paper. Okay, so there's 3 components, the aerated lagoon, the blower, and the pump, and we need to find out how each of them have changed in price over time and because of the larger size of this system we're trying to predict. So it looks like the blower, original one, was $385,000, and we're going to project $773,000 for the larger one. The aerated lagoon was $3.3 million. The new one will be $12.4. The pump, the old one was $121,000. The new larger one that will be built, $291,000. So the cumulative cost estimate for those 3 things added together is approximately $13.5 million. So this is really closely related to one of the homework problems that you've got. I think you should be able to sail through that using this in-class exercise as a guide. Any questions before we continue on? Okay, we've got 2 other things I want to introduce, so we'll have to move quick. There's the factor method, where what it says is that the cost of an entire project is usually some multiplier or a factor of a component which is a major cost factor for the project. So as an illustration, one thing I've noticed in my own time is that like you didn't necessarily have to look at the full menu of a restaurant to know whether it was going to be an expensive restaurant or not. You just had to look at the cost of one thing, a bottle of water. And so if you go to a restaurant in Dubai and look and see that a bottle of water is 3 dirhams, which is less than $1, then the whole meal is usually about 10 times that as much. But if you go to a restaurant and you notice that they're charging 20 dirhams for the water, that's an indicator that that's an expensive restaurant, and the whole meal is going to be about 10 times the cost of the water bottle. So that's just like a conceptual illustration, but the same thing can be applied in the real world to a lot of other cost items as well. Now we can go into a little bit more sophistication there, and we can look at what is the cost of an item when taking into account the major equipment, but then also adding on indirect cost factors. And so a major piece of equipment is going to be representative of some fraction of the cost. Like for example, the in-class exercise that we've got, I'm suggesting that a diesel generator is just part of what, the direct cost of the diesel generator is just part of the overall expense for getting a backup power supply system for a building. It would include the backup diesel generator itself, the cost of a concrete pad, the cost of training for the item, and so some percentage of the major equipment cost is added as a direct cost factor, so it's expressed as a decimal. And in the in-class example problem, we're saying that the concrete pad F value, that's a direct cost factor. It's saying usually the concrete pad costs 39% of the diesel generator. And operating training is found to be, over time, approximately 16% of the cost of a diesel generator. And so you add those all together, the cost of the generator itself, and then all of the other direct costs. And then on top of that, add in the indirect cost factor. So the indirect cost factor takes into account things like the department that ordered the equipment, the accounting department that's going to be balancing the books, the people who manage a grant or who are in charge of client relations and go out and get business for your company. So those are all factors which have to be covered by the total cost of the equipment, but need to be added on after accounting for the direct cost factors. So in this example, what we'd say is that the total cost C sub t, so C sub t is going to be the cost of the major equipment, which in this case is the diesel generator for $750,000. No, I'm sorry, $975. So $975, and then we add on, the 1 is to ensure that the cost of the generator itself is accounted for. Plus we add on the concrete pad, so 0.39, plus adding on the cost of the operator training, 0.16. And then we close the brackets there and add on the cost of the indirect. So 1 plus 0. Indirect cost here is 27%. Okay, so this would allow us to find out the overall cost of putting this backup power supply into service. So in this case, if you multiply the generator by the sum of the direct cost factors, what you'll get is $1.5 million in direct costs. But then you have to also add the 27% for indirect costs, and that brings the overall project expense up to $1.9 million. Any question about that technique? Okay. So what are direct costs versus indirect costs? Remember, we've talked about this before. The direct costs are those which you could directly tie to the production of some output. And so you know how much of this input is required for the output that's being generated. So you know how many hours of labor is required to produce a thing, whether it's a truck, whether it is a microchip. You know how much labor there is. You know the expense of the materials. the supplies that are used for manufacturing and packaging and so on. But then there are other things that are just general expenses that can't necessarily be allocated on a per item basis to the direct production. So they're classified as indirect costs, and we recover them as some percentage. So indirect costs can be hard to assign to a specific output. Like, you don't necessarily know if you're producing more than one thing. Let's say that your company is producing both cell phone cases, but also fidget spinners and cell phone chargers. Your company is producing cables to connect cell phones to chargers and so on. So you've got a variety of different supplies. It can be hard to know how much of the rent should be recovered through sales of the cell phone cases. How much of the rent should be recovered due to the production that you're doing of the cables themselves. So there has to be some way to account for and recover indirect costs if you're producing a variety of outputs. So it's hard to assign how much of the indirect costs should go to which output product that's being manufactured. And so because they have to be recovered, there are a variety of different techniques or suggested bases for allocating things. And so, like, if your company has to pay property taxes and you're trying to decide like which division of the company has to pay how much for the property taxes, well, the division of your company that's taking up more surface area should pay a higher proportion of the property taxes than the division of the company that isn't using as much space. So one way that you could allocate how much of the taxes need to be covered by which subdivision of the company would be how much space are they each occupying. So each of these different cost categories, there's a suggested basis for how you could know how much of the costs to recover. So if, for example, you've got a university and they subscribe to Adobe Creative Suite. So you've got some software. Should every student at the university pay the same amount for the Adobe Creative Suite? Or should you base that expense on who's actually accessing that software? And so if it's related to accessing, then it could be maybe that the College of Arts and Media has a higher lab fee than students in the College of Education who don't use the same expensive software. So ways to recover those costs should in general be related to how the costs are incurred, if you can draw a relationship to it. It may not be on a per unit basis, but you do know generally some measure of who's using a certain thing and generating the associated cost. So cost centers are the products or services of the company, and they cost your organization something in order to produce. They're going to generate revenue when they're sold, and because they're going to generate revenue, what we do is we allocate indirect costs to those cost centers so that we can charge more than just the direct expenses, that we can account for all of the costs of producing the certain item. So activities there are a lot of departments that provide indirect support, like purchasing, quality control, the IT department, supervisors, and so on. And they generate the indirect costs. That's what needs to be covered by the cost centers, which are ultimately going to generate revenue. So what drives the cost is how much is actually being consumed of a certain resource. So it could be the number of items that are being expected is what causes a quality control expense. And so you're trying to figure out which products that are being sold should be charged for the items that are being inspected. So these drivers, activities, and cost centers are what we're trying to account for in something like this last question on the in-class exercise. So if you turn to part 3 on the second page in the handout, there is a college that has 3 departments, an engineering department, a safety department, and computer science. And we've got some of their characteristics, how many faculty members they've got, the number of students, the computers that they have. and then how many support calls they generate each week. And what we're trying to determine in this example is if you're trying to pay information technology to cover their budget of $145,000, how much should each of these departments chip in? Like, would you just divide the amount by 3? Well, that wouldn't be a very fair or justifiable basis just to say each department has to contribute the same amount of budget to IT department. Maybe it would be based on the support calls per week. And so in part A, what I'm going to ask you to do is think of what if you're going to add together all of the support calls. And so 5 plus 6 is 11 plus 2 is 13. So there's 13 total support calls each week. So according to this method in part A, we're saying that the computer science department should pay 2/13 of the IT budget. So we're saying CS should pay how much of the $145,000 is their share? It should be the number of support calls that they generate in a week divided by the total number of support calls, 13. So if you multiply 145,000 by 2/13, then what we get is if we use this approach, then they should pay $22,307.69. Okay? So we want to do the same thing for the safety technology and engineering. And that's technique A, allocating it on the basis of support calls. But maybe there's an argument to be made just that the costs are driven by the number of computers, not by the number of support calls. And so a similar approach in part B is going to be basing it on the fractional number of computers that they have in each of those departments. So you add up the total number of computers in all 3 departments, and that's going to be the denominator of the fraction, and the numerator is how many computers are there in that individual department. So let me pause and let you work through these 3 different techniques. Which of these methods do you think the safety department would be the most upset with? Which one would they not like?
Computers.
Yeah, just by going by the number of computers. And so, like if they were in some sort of a budgeting meeting with the dean, what they'd be saying is, well, it's not the number of computers that drives the cost. It's they'd say, oh, no, they wouldn't like support calls because that gives them the highest cost. Like, this is an amount that they're going to have to pay. So they don't want to pay $66,000 to the IT department. That's how much they'd have to share of the budget. So the safety department would say no to the support calls method, and what they would like is the number of computers method, because that means that they have to contribute less to the budget. So what would be the right way? Probably a blend of these 3 different methods, because all 3 of these things are what drives the IT department interactions. It's partly about support calls. It's partly about how many computers you've got, how many students there are. So this is another one of the techniques that I think is included on the homework assignment. Okay, so I'll see you on Monday. Hope you have a great weekend.